Good morning. We are going to talk about rational functions today and non-permissible values. A rational function is a function that can be defined as a polynomial divided by a polynomial. Now remember, our definition of a polynomial is a function that can be written as a x to the n plus a2 x to the n minus 1 plus a3 x to the n minus 2 plus etc. Till we get to x to the 1 plus a to the power of n. So we have to have those exponents being whole numbers, including 0. So 1 is, or a constant is a polynomial. So we are going to look at those things that have a polynomial divided by a polynomial. Now, there is a mistake here, so please fix this, where g of x, where the bottom polynomial cannot equal to 0. Dividing by 0 gives us a number that's undefined. We don't have a definition for that number. And that's what we're going to do. In this case, we have four functions, I guess. We have values that are non-permissible. I cannot have x minus 3 equaling 0. Therefore, x cannot equal to 3. X cannot equal to 3. Over here, x minus 2 cannot equal to 0 because then we're dividing a value by, or a number by 0, which is undefined. X cannot equal to 2, and on this last one, x cannot equal to 4, and x cannot equal to negative 2. So the domain of each of those functions, okay, the domain of this function is x is a set of the all real numbers where x cannot equal to 3. Now if we go full on set builder notation, there's the proper set builder notation. This one would be x such that x is all real numbers where x cannot equal to 2. Over here, x is such that x is all real numbers where x cannot equal to negative 2 or 4. Now for this one down here, I of x, a little harder to see what numbers can't be used. But if we recognize that this is a difference of squares factor, and now we factored out the denominator, now we can see that x cannot equal to minus 3 or plus 3. And again, our range, or our domain, x is such that x is all real numbers, where x cannot equal to plus or minus 3. Now we're going to look at what happens to these guys as we approach those functions, or as we approach those non-permissible values. What happens? There are two processes that happen. So for this guy here, we have two values. X cannot equal to 3, x cannot equal to negative 1, and down here, x cannot equal to 3. Now our domain for the f of x, now I'm going to write this in interval notation, and it'll show you why I don't use interval notation very often for this type of domain. We go from negative infinity to negative 1, or negative 1 to 3, or 3 to infinity. Now, it's a little cumbersome. I've got three separate domains. Now, instead of the word or, what's probably going to show up is this symbol. Looks a little bit like an upside down U. It stands for union, and it basically is or. I tend to use set builder because it's so much easier. g of x is such that x is all real values, or x does not equal to 3. Now, if you get your calculators out, and we're going to enter this first guy in, and then we're going to look at the table set, which is our second window. So here's our calculator. Let me just move that the heck out of the way. And I'm just going to go over here. I've got the two functions that I want to look at punched in, but I don't want to look at the second one now. So I want to go to second window, and I want to go to table set. So I'm going to start at 1.5, and I'm going to go up by 0.1s, and then I'm going to go look at my table. Now we can see what happens to our graph here. As we get closer to 3, we're starting to go down. If we look at our table set, another way of seeing that, starting at 1.5, we are at negative 1.2, we end up with negative 3 at 2.5, and as I get closer, 2.6 is negative 4 almost, 2.7, negative 5, 2.8, negative 7, 2.9, negative 15.31. If I go back to my table settings and I just tweak them a little bit, 0. I go by 0.01. Oops. Stop that. And I go at starting at 2.9 because I really don't see like going that much. And I go back to my table set. Well, we knew it was at 15.8, and then if we keep going, you see it gets very small or very large negative numbers until we get to 3 where we see an error. So that is our undefined value. Now what we have here is, and if I was to look at the other side, so I'm just going to go to the other side of this, and I start to approach it from the positive side. Here we can see that we're at 3.01 is big number, 3.02, and you're getting smaller and smaller as we get farther away from, As we get farther away from 3, our values get closer and closer to, 0 in this case. So we have what is called a vertical asymptote at 3. We also happen to have a vertical asymptote at 1. Okay? So there's a line drawn vertically at x is equal to 3 that this graph is getting closer and closer to, but not touching. So one of the discontinuities in this graph is a vertical asymptote. So that's all this one has. Now, if I look at my next graph, and I'm going to go back to my table setting and go back and start it again at 1.5, and I'm going to go up by 0.1, and I graph that second table. What we see here is, okay, 2.5, just like we were expecting, we're increasing by 0.1 each time. Now, if I go down, as I get closer to 3, everything seems to stay the same. Everything's getting closer by 0.1 until I hit 3, which is an error. Now, if I go back to my table settings and do what I did before, go by 0.1 starting at 2.9. We're now going up by 0.1. So what we see here is it's getting closer and closer to 3, getting closer and closer to 4, which is our output, but it doesn't hit 4 as an output. We get an error at 3. Now, if I go to my graph and I zoom in a little bit, can't really see what happens here, but if I go to zoom square, everything should actually work out where we can see this. I guess not. I'll have to do a bit of zooming in. If I get close enough to this, it's going to actually show me what happened at that point. I guess on my graph it doesn't. But if I go trace, and I hit trace 3, I see why it's just a little bit off with my windows. So trace 3, hit enter. We see we get no value for our y. Why is my cursor not showing up here? Now you can see that again. I don't know why my cursor isn't showing up, but this lack of a y value down here shows us that we have no output values for that. This is what's called the second form. It's called a point of discontinuity. So what we have for this one is we have a straight line till we get to 3. And at 3, we have a hole in the graph. So that's the point of discontinuity. With our original graph, or with our first graph we talked about, we had 2 vertical asymptotes. I think the graph looked like this. So those are our 2 points of, or two discontinuities in this graph. So we can have a vertical asymptote and we can have a point of discontinuity. Now look what happens if I actually reduce this g of x. G of x reduces down to x plus 1, which is what that line is, but x cannot equal to 3 because our original guy had a non-permissible value of 3. So g of x does reduce down to x plus 1, but there is also that discontinuity that we have to take into account. So at x is equal to 3, we have a point of discontinuity. With f of x, we can't cross off any of the denominator parts, any of the factors in the denominator. Anytime you have a factor still left in the denominator, you're going to have a vertical asymptote as the discontinuity. So we want to identify if they have a vertical asymptote or a point of discontinuity or both. And then we want to find the point if it has a point of discontinuity. And we want to give the equation of the vertical asymptote. Well, if I look here, f of x, x minus 1 times x plus 2 over x minus 2, x plus 1. I am not able to reduce this any further. Nothing on the top crosses off with the bottom. So we're going to have a vertical asymptote. We're going to actually have 2 of them at the discontinuity where x cannot equal to 2. We're going to have a vertical asymptote with an equation of x is equal to 2. And since x cannot equal to negative 1, we have a vertical asymptote at negative 1. So that gives me a starting point to sketch my graphs. So now here we have an x minus 3 squared on the top and an x minus 3 on the bottom. So that guy and that guy are going to be able to cross off. So g of x simplifies to x minus 3, x plus 2, where x cannot equal to negative 2 and 3. Now, we still have that guy on the bottom, x plus 2. So what we have is a vertical asymptote at x is equal to negative 2. Sorry, x is equal to negative 2 because we're describing the vertical asymptote. We would describe the point of the discontinuity where x cannot equal to negative 2. But we also have a point that has an x coordinate. So the point of discontinuity is going to have an x coordinate of 3 something. We want to describe that 3. Now what we're going to do to that is to plug it into the simplified form. Because if I plug it into here, I'm going to end up with 0 over 0. Because we're going to have x is 3 minus 3 over 3 minus 3. And I don't care, that one doesn't worry because it's 0 times some value. So plug it into the reduced form. So we have 3 minus 3 on top over 3 plus 2. Okay, that's 0 over 5, which is 0. So in this case, our point of discontinuity is going to occur at 3 and 0. Okay. Now this one here, it's a bit of a trick. We see our non-permissibles are x cannot equal to 1, x cannot equal to 2/3. Okay. Now we can't, it doesn't look like we can cross anything off, but we actually can. Because if I take out a negative 1 from the bottom there, that'll give me x or minus 1 plus x. Now I get to cross that guy off, leaving us with h of x to be x plus 2. I'll bring the negatives to the top over 3x minus 2. So, and then we have x cannot equal to 1 and 2/3. So those are our non-permissibles, negative 1 or 1 and 2/3. We have a vertical asymptote where x is equal to 2/3. He's still left in the denominator of our function. So that's anytime something's in the denominator in your simplified form, that's a vertical asymptote. We have a point of discontinuity where x is equal to 1, and we have to figure out what the y value is. So again, taking 1 and plugging it into your simplified form of h of x. So we have negative 3 over negative 2. No, sorry. Negative 3 over 1. So negative 3. Our point of discontinuity, and this is terrible border, 1 and negative 3 is our point of discontinuity. Now, what we're getting here is we're starting to do our basics of curve sketching. How do we curve sketch without using this thing? Okay. And that is one of the skills that in math that we are going to use quite often. So I will go over the whiteboard work with you in class and give you some time to work on the homework for the rest of this. I shall see you later on.